environmental trade-offs of roof-mounted solar plants for manufacturing locations in the US. Thank you. Welcome.
Thanks for the introduction. Hi, everyone. My name is Amir Namin. I'm a PhD student at Environmental Benign Manufacturing Group at Northeastern University. Today, I'm going to talk about the comparative analysis of economic and environmental trade-offs of roof-mounted solar plants for the manufacturing locations in the US. So first question is, why is it important for the industrial sector to consider renewable energy? So globally, industrial sector is responsible for 33% of primary energy consumption and 37% of greenhouse gas emissions. International Renewable Energy Agency, IRENA, developed a roadmap called REMAP in 2016, which targets a certain level of renewable energy consumption by year 2030. This plot, which is developed by IRENA, shows the US energy consumption by industrial sector. On the vertical axis, we have the energy consumption in petajoule. The first bar here shows the energy consumption of the industrial sector at 2010. So if we move forward with the business as usual, the same conditions at 2010, so we will get to the second bar here, which shows the energy consumption of the industrial sector at year 2030. But the percentage and the rate of renewable energy consumption remains the same at the level of year 2010. However, the roadmap shows that we need a significant improvement in the amount of renewable energy consumption from 12% to 34% by year 2030. The question here, can renewable energy be implemented cost effectively? On this slide, I would like to quickly touch on the Paris Agreement, the agreement which US stepped out a couple years back. So the backbone of the Paris Agreement is dealing with the greenhouse gas mitigation, adaptation, and finance to limit the global warming level below 2 degrees centigrade. But there is a big if here, if all NDCs, nationally determined contributions, fully implemented. Therefore, reports showed that there is a need for manufacturing firms to engage in voluntary climate actions to meet the greenhouse gas reduction target. However, 2018 global assessment of the industrial sector showed that we are not on track to meet the limit of 2 degrees centigrade. In 2015, US Department of Energy reported that less than 2% of the required energy for the industrial sector generated on-site through renewable energy resources other than biomass. This US map here, which is created based on the MEX Manufacturing Energy Consumption Survey database, shows the industrial emission by state in 2018. So as we can see, Texas, Louisiana, California, and Indiana here are among the top 4 states in terms of industrial emission and energy consumption consequently. So all this information together clarify the need for strategies that we need to reduce the industrial energy consumption and greenhouse gas emissions. Here we have some of the strategic advantages of having on-site renewable energy, including the reduction of greenhouse gas emissions from fossil fuel-based electricity generation. Improving the reliability of power sources is a really important factor for the manufacturing and industrial sector, and also its potential to be economically feasible. Some of the advantages of having solar energy on site are including decreasing capital cost and efficiency improvement during the past few years, and also the flexibility of installation. So all these advantages together motivate some of the manufacturers to invest and to consider solar renewable on site. One example here is steelmaker Evraz, which is a really high energy intensive manufacturing. They are based in Colorado. They developed 240 megawatt solar farm, which can lead to the early retirement of 660 megawatt of coal-fired generation by year 2025. And also we have Tesla Gigafactory in Nevada, which powered 100% by Tesla solar. This plot here shows the electricity demand intensity for US industrial sector. On the vertical axis, we have 20 three-digit NAICS subsectors that explored in this plot. NAICS stands for North America Industrial Classification System. And on the x-axis, we have the electricity demand intensity in kilowatt hour per square meter per year. We use the MEX database on net energy demand and average enclosed floor space for each industrial sector in the US to find the range of electricity demand intensity, which are presented by these red bars here. And for the supply range, we used an energy software modeling tool called SAM, developed by NREL, National Renewable Energy Lab in US, to find the potentials of each single state in terms of electricity generation from solar PVs per unit area. And that presented by the green box as a supply range here. So if we compare the supply range with the red bars, which shows the electricity demand intensity, we can get a benchmark to see which industrial sector can rely or can use solar PVs as an alternative for their electricity need. So overall, we have 12 subsectors here that can meet their energy demand intensity through solar PVs. And from among these 12 subsectors, we're going to get a closer look on sector 335, electrical equipment sector. So with the focus on electrical equipment sector, we consider 1.75 megawatt rooftop solar system. This is the largest system that can fit on the rooftop of the electrical equipment sector based on the enclosed average floor space that reported by Manufacturing Energy Consumption Survey database. In this case study, we investigated levelized cost of energy and economic payback time as our economic metrics. And for environmental metrics, we explored price of CO2 equivalent abated, NOx and SOx emissions avoided, and energy payback time. We picked 5 states: California, Florida, Indiana, New Jersey, and Texas. So as you remember, California, Indiana, and Texas are among the top 4 states in terms of manufacturing emissions and energy consumption. New Jersey provides the most aggressive or most generous financial incentives for solar PVs in the industrial sector. And Florida also provides the high solar insolation. This table presents more detailed information on these 5 states. For instance, in terms of the number of manufacturing firms and employees, California and Texas are the top 2 states in US. And for the solar grade, New Jersey ranked A, California ranked B, and the rest of the states ranked C in 2018 by State Solar Power Ranking Report. To simulate the solar cost and location-based feasibility, we again used SAM System Advisor model. So these are the inputs to our simulation, to our energy simulation model. We can categorize the input into 3 groups: financial parameters, including tax and insurance rates, financial incentives, and regulatory policies. We have general information as weather data, PV types, and inverter. And also cost-associated factors like PV cost, balance of system, operating, and maintenance costs. So we feed all these factors into our simulation model and then get our outputs as the economic metrics that we explored. We also could find the annual energy generation in different locations. And then by using the sub-region e-grid emission factors and a meta-analysis and other literature on the cumulative energy demand of the solar PVs, we could explore the environmental metrics in this case study. So here are various assumptions for the input parameters. So I don't want to go to further detail on this. This table shows the various incentives and policies that are available based on different locations. So some of these incentives can be available in one location, but may not in the others. So based on the different levels of these incentives and policies, which they are absent or available, we looked at explored the options in different scenarios. This plot here shows the economic payback time under different conditions for the states. So on the vertical axis, we have the payback time in year. X-axis shows the different states. The darker bars shows the existing conditions for different states that we have. And also the light blue bars shows the conditions when we impose New Jersey conditions as the best condition to all the states. So under the existing conditions, New Jersey can outperform other states of around 3 years of payback to pay back the initial investment. And when we impose the New Jersey conditions to all cases, Texas and California are very close, but California can perform better by around 1.9 years. This table shows the levelized cost of energy for 3 different scenarios: existing conditions, absence of incentives and policies, and New Jersey conditions. So under existing conditions, again, not surprisingly, New Jersey can outperform other cases, followed by California because of the generous financial incentives in that state. When there is no financial and no financial incentives and policies are available, so all the levelized cost of energy would be higher than the current cost of energy. So that means technically the investment won't be profitable in all cases. And when imposing New Jersey conditions to all cases, Texas can perform better, followed by California this time. And these are the results for 1.75 megawatt solar facility for 25 years of the study period. This table shows the energy payback time. So we used cumulative energy demand for the life cycle of solar PVs. And on average here, we can see all the states can pay back the energy in around 1.5 years. However, California and Texas can perform better and pay back the energy faster. This plot shows the cumulative emission abated. On the vertical axis, we have the metric ton avoided per facility. X-axis again shows the states. The black bars shows the reduction in SO2, and the gray bars shows the reduction in NOx emission. Texas can benefit from reduction of SO2 at the highest level, and follows by Indiana. However, Indiana overall can benefit most in terms of the reduction in cumulative emission in terms of NOx and SOx. We also ran sensitivity analysis for the economic metrics that in this study we explored. So the variables we explored, including the solar module cost, labor cost, operating and maintenance cost, electricity price, and discount rate. So this plot here shows the annual savings from electricity bills in different states over a 25-year period. On the vertical axis, again, we have the annual dollar amount saved in thousands. X-axis is the year, so we can see that California can save the most in terms of the electricity bill, followed by Texas. But here, the largest range belongs to the state of Indiana, which shows the variable that we explored for the sensitivity analysis have the highest impact in the state of Indiana. For more detail, I have the results for the state of California here. For the economic metrics that we explored, for economic payback time, we can see that the operating and maintenance and module price have the highest impact on the payback time, while discount rate has no impact on it. However, levelized cost of energy is highly sensitive to the discount rate, while electricity price escalation has no impact on that. So as a summary, we saw that 1.75 megawatt solar can be most economically feasible under New Jersey conditions because of the most generous production-based incentives available in that location. We saw that economic viability can happen at the location where it's not always clear and sunny, referring to the results of the state of New Jersey. Smaller manufacturing facilities could realistically rely on on-site generation of solar energy. However, they have to pay attention to the locations that they wanted to choose. So among the 12 sectors that can practically rely on on-site solar PVs for their electricity generation, we picked the highest energy intensive sector. So that means other 11 subsectors can practically rely on solar energy for their required electricity generation, but they have to, again, pay attention to the locations that they wanted to pick and move forward with. And at the end, the current carbon credits are not adequate to significantly alter the economic results and economic metrics we explored. So that means if the policymakers and decision makers wanted to motivate manufacturers to consider renewable energy, they have to reassess and reconsider these policies and credits. Thank you so much for your attention. Right on time.
Well done.
I'm glad.
So we have a question. I'm just going to ask too. So what would be your recommendation for incentives or to policymakers? What would it be? Price on carbon? What would be the first thing that you would recommend based on all of those
Price of carbon can be one thing, and also in terms of the financial incentives that are available right now and regulatory policies, net metering and production-based incentives have the highest impact on the investment. So they can also reassess or increase those types of incentives.
Thank you for the presentation. What did you try to analyze at what cost the carbon tax would have an impact on the results?
So the current carbon tax, which ranged between $2 to $14 per ton, it's not adequate to alter the economic results.
But did you play with that parameter?
No, we didn't play with that. That can be a future work to play with that to see what type of, because the current conditions as incentives and policies that we have, they might change in the future. So, but by considering the current conditions, we can play with the carbon tax to see what range of that tax can be economically beneficial.
Okay, I'll come around. Don't forget to introduce yourself, please. Thank you.
Could you please back to the slide? Oh, sorry. I'm Felix from Smart Singapore. And could you please back to the slide which shows the payback time? I think it's like 3 years, right?
This one?
Previous slide. Next one? Yes, is this the payback time?
It is energy payback time.
Oh yeah. So which means for example, for California, the average delay is like more than 1 year. We can earn the money, right?
It's not the money; it's energy. So so here we have the cumulative energy demand for the life cycle of PVs.
Yes.
That we put to manufacture, transport, install, balance of system, operate, and maintenance. So we can pay back the energy amount in around 1.5 years.
Okay.
But this is the economic payback time, if you're looking for that. So for instance, in New Jersey, we can pay back the initial investment in around 3 years by the current conditions. But in California, it's more, it's like 4.5 years.
Oh, yeah, if in this case, the result should be reasonable, yeah.
Yeah.
Okay, thanks.
Okay.
Thank you. Very good presentation. Thank you.
Thanks.
Did you guys play with return, EROI, energy return and energy invested values?
No, actually, that's a really great suggestion. But we looked at the we looked at the price of the CO2 abatement per ton, which to be able to look at that, so we need the net present value of the investment. So we use the net present value to find the price of the equivalent of carbon per ton. Per ton. But the results are not in the slides because of time constraints, but it's in the
usually EROI, energy return on energy invested, are very low, particularly for solar.
Yeah, that's a really good suggestion. Yeah, thanks.
Have we got time? Or maybe we might. Anyone else? No? Okay. Thank you very much.
Thank you.
And if we can hand over the microphone, Alexandre. Yeah. Oh, you've got a mic perfectly. We've got a second one, so that's great. He's got one already.